quadrature encoder. We talked about those, right? What does a quadrature encoder do for? But it's not my problem, right? Huh?
Exactly, yeah.
So I forgot how much we pay for these things, but they're pretty neat. I can't remember who we got them from, but they're really neat. Yeah, if I can get it. Yeah, what I have, that's a good one. So here's the formulas, but I would, like me, you notice I didn't use the formula, right? I just did what? Well, I used the formula, but I figured it out, right? You understand? And that's what we like y'all to be able to do, because you won't be able to use a formula sheet on the test. So y'all have, and there's going to be one on the test where you're going to have to measure a sine wave, and it's going to ask you what the frequency is, and it's going to ask you what the frequency is. Let me get my scope probe back over on the function calculator. And it's going to ask you what the volts are, what the volts. So the two things, they're not going to give you the trigger. The triggers has nothing to do with making the measurements. All the trigger is, all we use the trigger for, if I look at the waveform and it's snaking all around on the scope, it means it's not triggered, is what we say. And then on this scope is really neat, so you can move it and just get it inside your waveform, right? You understand that? Oops. So what's my voltage and what's my frequency for this waveform right here? So what's the voltage? By the way, we call this voltage between here and here, we call it peak to peak. We call this voltage peak. And it's a sine wave, so if you look, this guy right here, this and this is exactly the same thing, but they're the mirror images of each other, right?
20 volts? 10.
Well, we got it on how many volts per division? 5. How many divisions do we have? 4. So that, you're right, that'd be 20 volts, but it'd be 20 volts peak to peak, from peak to peak.
So in general, when I ask for volts, it's talking about peak to peak?
Peak to peak. Now, most of our formulas deals with V peak, so RMS would be this peak voltage. So I could take this peak voltage right here, which is 10 volts, and I could multiply that by 0.707. I could put my meter on that and put it on AC, and that's what it would measure. So that would be what RMS is, the work we get, right? RMS is the equivalent of the DC that would be the same. So 10 volts RMS would do the same work as 10 volts DC into resistive loads. Now we're not going to go any further than that. I think I'll take AC and you're going to find out that AC is weird. And then what would my time be? So my time, I have it on 50 microseconds per division, right? You understand that? And I've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. So what would that be? That'd be 500 microseconds, right? Then I would take the reciprocal of that, and that would give me the what? That would give me the frequency, which should be about 2 kilohertz. Why do I know that? Because this is a computer and it's doing the math for me. I should take this off, but you can always check your work. So you can, these digital oscilloscopes, you can make them do a lot of the work for you. So it will measure peak to peak for you, and it will give you the RMS value for you. But the problem is that you might not get it out there, and you might not get into a $450 scope, right? You understand? So I can get a scope that does this. I can get an analog scope that does this. It's a lot bigger, but for half that price. And it don't do the math for you. So it depends on where you get. But if you're going to deal with these encoders and stuff like that, then you're going to have to use an oscilloscope, because your meter's going to do it's going to average all that out, right? You understand that? But depending on what we call them. So y'all okay there? Y'all can do that? So what do you need? You need to know the volts per division, right? So you need to know the watt, the volts per division, and you need to know the time per division. You'll find that it'll either be given to you on the test. It'll say what would be the peak to peak voltage if it's set 5 volts per division, and then you can just count the number of vertical divisions, right? You understand that, and multiply it by the volts per division, and then it'll give you the time. So to count out the time for the cycle, you'd measure the cycle, right? You understand? And then you can multiply it by that, and then you have to take the reciprocal of it to get the frequency. Let's see, there's something else on there I wanted to talk to you about. Oh. So we okay so far? Mind if I turn this on? And what we need to do, guys, is we need to get to the mechanical. All we got to is gears. Are everybody okay with the gears? Yes, no? Yeah, the modulus. So what's the modulus? The modulus gives us an idea of what the gears would mesh. That means their teeth and everything, and then you have to consider the horizontal width, right? And then planetary gears. And then we have what they call a gearbox, and basically a gearbox or gear train. Some of you guys heard call it. Basically, this is multiple gears inside a single. So we'll just draw that. I'm just going to draw these gears vertical. So this is my driver, and then I'm going to take this and go to a smaller gear, and then I'm going to come out of this guy, and then I'm going to go over here like this, and I'm not going to put the shafts. They would have shafts on them, of course. And this, I didn't draw that quite right. Because it was supposed to be in the center of the thing. So let's say this guy right here had like 12 teeth, or let's use diameters. And of course, the centimeters and meters don't make any difference, right? As long as you keep the same unit. And let's say this right here. Nope, I'm doing this backwards. Hope y'all have a pencil with an eraser on it, right? So I want to do a torque multiplier. So my driven is going to be a small one. So let's say this one had 12 teeth, and this has 24 teeth, and then this one has 18 teeth, and this one has 30 teeth, or diameter. So are we going to get a mechanical advantage out of this? Now, mechanical advantages, we know if we come up with a fraction, we know that it's a speed multiplier, right? And if you come up with a whole number, we know that it's a torque greater than 1. I should say that. That was off our video. Y'all remember that on the video? So what would this be? Well, we're going from little to big. We're going from 12 to 24. So anytime we go from little to big, it's a torque multiplier, right? And then here, we're taking that over here, and we're going from 18 to 24 over here. Right? You understand that? So here we would get a torque multiplier of what? 2. Let's make this 15 to make it easy. Here we get a torque multiplier of what? 2. So what would be my total torque multiplication? Huh? 4, yeah. So my output would be running at 1/4 the speed, but we'd be creating 4 times the torque. So that's what you'd have to do on a gearbox. You need to know the ratio. So if you went into this guy right here, you could calculate that if you knew the number of teeth. This is actually a 5-speed transmission right here. I don't know who put it out. What they do is they literally do what? Just shift the gears around and move them in. They start off with a really, really high torque multiplier, and then speed, and we talked about that, right? When you start off, you hear your engine running real, especially people that have stray shifts. You know, you can really hear that engine rev up, before your shift, but you're not going any speed at all, because when you start your car up, you want a lot of what? Torque. And then you start dropping the torque down by just shifting the gear ratio. Now, what type of gears are these? I don't know, it looks like this might be a spur gear. Okay, go ahead and take a break.